TV from other dimensions has a somewhat looser feel to it.
Yeah, it's got an almost improvisational tone.
Hey everybody, we are live right now. How's the audio sound? How's the video? Can everyone see me? Can everyone hear me? I think we're good. We've been streaming for a while now, so everything should be all right. Did I put this on ultra low latency? I did put it on it. Can everyone hear me? Can everyone see me in the chat? So I think we're on ultra low. Please tell me I put this on ultra low. It's great, everything's great. So okay, we're good. So, okay, wait. I want someone to talk to me for a second. I want to make sure we're on ultra low latency because that's my only fear because I hate it when we don't put it on ultra low latency. Who wants to be my helper right now? One person's going to be my helper. Who's going to be my helper? Who's going to be my helper? This will almost tell us. Okay, good. Caitlin, you're going to be my helper. Ready, Caitlin? Caitlin, here's what you're going to do. I want you to type SNAP in the chat. I want you to type S-N-A-P. Got it? So you're going to type it, but you're not going to hit enter. So does that make sense? I'm going to snap. So, oh, I should put it on. I'm like, oh, you're right. It's in the link stuff right there. Let me do that real quick, Adriana, too, while we do that. Thank you for that advice, because we'll do that here, too. So you're going to have snap typed in the chat, and when then you hear me snap, you're going to hit enter. Ready? So when you hear me snap, you'll hit enter. So have it typed. Don't be typing when I do it. You ready? Oh, that was a bad snap. Good. We're on like a 4-second delay. I like that. We're on ultra low. If we're on regular latency, it's ridiculous. It's so long. So I'm going to go to the videos. 2 seconds. We're getting started up here. People will be coming in. Good to have everyone here today. Exam 2 currently live. So let me grab this video, copy link address. Let me two-factor authenticate. How's everyone doing today? Oh, you like the intro? Yes! Dylan, I'm so glad you liked it. That's one of my favorites. Rick and Morty, November 10th, coming up soon. And so you get to take the test, and then you get some Rick and Morty goodness in your life. So we try to have some fun intros. We're on a 4-second latency delay. And I'm going to put this into two-factor authenticate right there. We're going to throw this into our online classroom because I did an announcement today, but I didn't put it here. So edit, and here we go. So have your questions. While I'm doing this, I want you to look up whatever you want me to go over. This is your review today, and you get to choose what I do. Who has a question? Who has a question to start class? Who has a question about what you want to understand, what you want to know? What do you want to understand, what do you want to know? Are we all good? Is this it? Is it like, oh, bye everybody? So what questions do you have? What questions do you have to start us out? I'm going to turn my volume down just a little bit here. I've got the mic a little closer to me today. Will you go over some of what the symbols mean in the equations? That's a great question. I like that question right there. Let's hop over to the notes over here. I've got some notes up and going. So we're going to hop over here and let's do some of the equations. So let's do it. Okay, so we're over here. I've got the test pulled up. Let's go to this sheet right here where it's got exam grade. We're not going to write our exam grade. I'll put 100 in there. Types of random, we'll do that next. Great question, CE. Put 100 for yourself, we're good. There, ace the test. We can go over some of the biases, we'll do those next. I like the symbols to start, that's a really good idea. Like Carolyn says, can we go over some of the symbols? Let's write down every symbol we can do. Now, here's what I want you to do. If you're watching this video now, especially in the future, every time we say a symbol, I want you to, one, write it down, and we usually put these in the back of our notebook so we can kind of flip back and be like, okay, what are the symbols? But two, see if you can name the symbol when I go over it. When I mention the symbol, see if you know what it is before I tell you. So like pause and be like, okay, do I know that? And you're reviewing while you're writing it down. So let's go over here and we'll take all these questions. Great questions. We're going to do symbols, then we'll do sampling, and we'll do some more. So here we are with n. Can anyone tell us what n is equal to? What is n? When we see n is used so much. It can be in a question like we went out and spoke to 500 people, or it could be like the mean of the distribution was 880 with a standard deviation of 2. This was taken from 200. What is n whenever we see n? N is sample size. Nice job right there. N is sample size. If you ever can't read my handwriting, please tell me. My handwriting gets a little bit sloppy sometimes, but that says sample size right there. Technically, and so Zach points something out, technically capital N is population size. So capital N is population size. I'm gonna turn it up just a tiny bit and tell me if it gets too loud or anything. I'm gonna turn it up just a tiny bit there. So now it's up a little bit higher and I'm hopefully not going too loud. Tell me if it's too loud or I start clipping with my audio. I'm gonna try to speak at a nice, calm volume at all times. So a little bit higher there. Is that better, Caroline? So we have N for sample size. The next one we get, let's do P hat right here. P hat, what is P hat? P hat, there's two things we should say for P hat. P hat is the what? P hat is the sample proportion. Adriana, nice job. Sample proportion. P hat is the sample proportion. Now you always want a nice job right there, Chung, great work, because everyone's getting the answers right and I like this. We have right here the sample proportion. And what does this mean? This would be in a question like, let's say we went out and talked to 100 students and 40% of them are from Tennessee. 0.40 would be P hat. Always think of questions and examples where you'd be using this notation, so you can identify it in a question. If we went out and talked to 100 students, that'd be N, and then 40% of them would be P hat, which is 0.40. But we can get here, from this, we can get Q hat. What is Q hat? Anyone have any idea what Q hat is? It's the what of P hat. I'm probably gonna misspell this one. It is the what of Q hat. While I'm giving these long pauses while they're thinking, boom, it's the complement. And that is found by 1 minus P hat. Now let's play the game. You ready? Great answers, Zach, Caroline, Adriana, keep it up. Just be trying to answer this, be writing these down if you don't know them. Take all the notation we're about to do. We're gonna try to name as much notation as we can to start, which will help us for later problems. We have here maybe 40%, I think I said, of students were from Tennessee. Then what is Q hat? And you can tell me 0.40 is Q hat, 0.40 would be, excuse me, P hat. Then what would be Q hat? If 40% of students are from Tennessee, 0.60. 60% of students are not from Tennessee. And this is what we did with probabilities. We would say you are either this or not this. Nice job, Jessica and Hunter and Caitlin. All these great answers in the chat right now. Keep these answers coming. So now we have P hat, we have Q hat, and what else do we have? Well, I'm going to change up colors here. Reason is because we're going to talk for a moment about Y bar. Y bar I put as a different color because Y bar is what? Let me do this. While you're thinking about what Y bar is, I'm going to rewrite this top one. What is Y bar? Y bar is the what? Y bar is what? What is Y bar? Sample mean, Jessica, nice job. Sample mean. What am I denoting with these differences right here? What you'll notice is we have some red ones over here, and the red ones are categorical, and the blue ones are quantitative. So the red ones are categorical and the blue ones are quantitative. So let's think. If we have the sample mean, we'd also need this. What is S? What is S? S is going to be what? S is, they're due tonight. There's some due next week. There are some due next week. You might be seeing the one that is due next week. There is some due tonight. Standard deviation for a sample. Sample, standard deviation. The sample standard deviation. I put in the new assignment, so it might have bumped it up as the newest one. There is an assignment due tonight, and I'll change the order so it's a little more clear, but there is an assignment due tonight, unless I made a mistake on the dates, but there is the assignment due tonight. And then there are some due, I think, Sunday and next week. So make sure, I just moved the one off Halloween. Hopefully I didn't change the order too badly. But we have here sample standard deviation. We have here, let's go here, P and Q. And that's not the red I want. I want the thicker red one. P and Q and mu, oops, wrong color. Mu and sigma. So if you notice, what I'm doing right here is I'm making a divide, where these will be for the sample, and these will be for the population. So if you put them in your order, if you put them in your book this way, you will understand which is for which, because P now is merely population proportion. And then this is just the complement of that. And then what is mu going to be? What is mu going to be? Think about the way I lined these up right here. What will mu be? What will mu be? The way I've kind of lined everything up right here to talk about it all. You're right, it's the mean, you're right. But what kind of mean? You are right, it is the mean. What kind of mean will mu be? What is mu? It is a mean, you are very correct. Population mean, you are right. This is the population mean. And then this would make this the population standard deviation. If you notice, a lot of times we use Greek letters for population parameters. It's not always, but population parameters often have Greek letters. Every population hates mopping, mu, sigma. Oh my gosh, I like that right there. Every population hates mu, sigma, pop, prop. I like that right there. So population parameters are right here. These are all population parameters. And then I've done some color coding for you so you can kind of see which goes with this. And hopefully you can read my writing. P hat is the sample proportion. Q hat is just the complement of that. And also we have 1 minus P is the complement of Q right there. So these are all the things right here. So these are how we use the notation. Does this help out a little bit with the notation? Does this make a little more sense? And you should be able to have these down and understand where mu, because it looks like an M, exactly, like an O and a P. Oh yeah, I see it now. I kind of see it. How are people doing on these concepts right here? Pretty good? I like it. That is a quick review of the notation primarily used on this test. I can't think of any other major ones. There are, here we'll go down a little bit further here. We've got a whole nother page area. So you will see things like, let's go right here and just write mu P hat is equal to P. What does this read? This reads that the population mean for the sample proportion is equal to the true proportion. So that's why when we do these problems, we'll draw out a curve, and if you have that P in a problem, if P is equal to 0.60, then at the center of this curve, you would put 0.60. This curve is for this right here. This is what the curve is for. This curve is this right here, but you're saying that the center of that curve, the mean of that curve, is equal to P. So that's what we're doing by saying the population mean, what we expect from the population of samples. So this is the population of sample proportions, which is very interesting. This is the sampling distribution chapter, but when you break it down to the population mean for the sample proportion, it's what you would expect to see if you took kind of an infinite amount of samples from a population. So when you break it down to what it says, the population mean for the sample proportion, or you could call that the true mean, or what we would expect for sample proportions is the true proportion. Does that, especially when you look at the wording a little bit more, you can just read this as what we expect to see when we take a sample mean is the true, what we expect to see when we take a sample proportion. What we expect to see when we take a sample proportion is the true proportion, and that's why that goes right there at the center of the curve. Does that make a little more, is that by P? Yep, so basically all, and let's talk about that just here for a second. If you hear me say true, true and population are kind of synonymous words. So if someone were to say to you, people might say like the true mean. If someone said the true mean, they're talking about for a population, and then sample just means for like a sample size. So true and population are synonymous words. It's like, this is the true mean, this is the population mean, because it's the truth for everybody. So they're kind of interchangeable words to say this is the truth or this is for the population. So you might hear me say true mean later on, and that's what I'm talking about when I'm talking about for everybody. This is the true mean, this is the mean we found in a sample. So true mean, and let's put a little note on that. Last little note, then we'll hop to some more topics. I lost my pen. There's my pen back. Let's go back to draw. And so we'll put here in parentheses true. It's just a synonymous way of calling it the population. Sometimes you can be redundant, which is not bad. You can say the true population mean, but that's why I often talk about the true parameter, because we're trying to understand for the population. So if you hear me say true parameter or like true proportion, I'm talking about for the population. So great job right there. Jackson, thank you for that great question. Is that by, so when, with P can be called the true proportion, and I hope that makes more sense. Any last questions about notation and how we kind of talk about stuff? Any other last questions? And thank you for everyone helping out. This is a really good review of notation, understanding all of these, having them written down. You're welcome, Jackson. Ask the questions. If I don't make it clear enough, just type it in again and I'll try to clear it up. I want you to understand what I'm saying when I talk through all these things. Population and true are synonymous words that can be pretty much used interchangeably. So let's do it. Could you scroll down again? Of course. This was just an example kind of talking through, kind of like talking about how we can talk about the notation, that the population mean of the sample proportion is equal to the true proportion right there. You're welcome, Hunter. So I think there were some questions on sampling. Was that the next thing people would want us to go to was chapter 10, sampling. Let's see. We could do you want to do the test problems on sampling? We've got some right here. It's pretty good test problems right here. A major airline, then we'll talk about some of the key concepts. Yes, we will do that, Caroline. We will definitely do that. So a major airline wants to find out if additional charges for baggage affects how the airline passengers choose to fly with and how often they fly. They decide to survey passengers who are flying on their airline. So that would be, what would this be? Let's break this question down. Let's do it with another color. They decide to survey passengers. What would that be? What is that in this question? They decide to survey passengers who are flying on their airline. So those are the people they want to understand. They want to talk to people who fly on their airline. What would that be? Well, you're thinking of sampling right now. So if they talk to, and this is how convenience would go, take this note. How about if they had someone who works for them talk to the first 100 customers they can find? That would be convenience. And I think people are looking at the question below. We're focusing in on the first part of it, like, close, Jessica, very close. This is the population. And then over here, they want to look at how additional charges affect them flying. This is the population parameter, sometimes called the parameter of interest. Let's break down what these words mean. The population is everyone you want to understand. The population is everyone or thing you want to understand. Does that make sense? Like, you want to talk to UT students about tuition. So their views on tuition is what you want to understand, so that'd be the population parameter, and the people you want to understand are UT students, making them the population. The population is every person or thing you want to understand. The population parameter is the thing you want to understand about them. Does that make sense? Population, every person or thing you want to understand. Population parameter, the thing you want to understand about them. Because we talked about a parameter being the truth, so this is the truth for the population. A population parameter is the truth, like the true mean or the true proportion. So that kind of narrows down what that preface is doing there, and always kind of read through each question for each additional bit of information to understand all this extra stuff we can know. So the airline decides to select 30 of their flights over a 1-week period. What sampling method is this? 30 flights over a 1-week period. And so I wish this question, because it should say, they're going to sample everyone on that flight. They're going to sample everybody on that flight. So this would be the what? If they sample everybody on the flight, this would be what? What is the answer here? The answer here would be clustering. In cluster sample, you take a large group at once. And let's do a little review of clustering versus stratified, because that's where I often see people getting confused. Let's go through all the sampling methods here so we can remember them. So our first and easiest, we should say easiest, and they said in the chat earlier, so I'm going to cheat with the spelling, convenience. What is convenience sampling? How could the airline do a convenience sample? If you can write your own test questions, you're doing great. How could the airline do a convenience sample? I said it earlier, and I want to see you say it in the chat. I want you to be thinking about this. I want you to be writing it down. How could that airline do a convenience sample? Easy to reach sample. Easy to reach sample. First 100 passengers to arrive at the terminal. Convenience. Everyone who boards the plane gets a survey. That might be an attempt at a census if they did it for everybody, total everybody. First 200 passengers they see, so they just say, just talk to the first 200 people. Or maybe they put it on the internet. That would be convenient too. That'd have a lot of bias. Does that make sense? Like if you just said, we'll put the survey on the internet and just let people respond to it. So sampling the first or doing it in a way like putting it on the internet. So that would be convenient. How about next we have simple, random sample. What is a simple random sample? A simple random sample. What do we have to do with the simple random sample? Well, I think we're going to go over to Word because I can write it out a little bit nicer inside of Word. Hey, it's our confidence interval interpretation. We like that. So let's go here to Word and let's write out how we do a simple random sample. Simple random sample. First thing we will do, give each passenger a number. Can't spell number or passenger. Give each passenger, it's got an E or two. There we go, a number. Randomly select from those numbers. So, and so that's how you pick them at random, right? Great answers right there, great job. We're gonna give everyone a number, and then we're gonna select those numbers at random. So all you have to do here is do, everyone gets a number. So imagine we have like people's frequent flyer IDs. So we take everybody's numbers, and then we select people at random. That's what we'll be doing right here. So this is a simple random sample. Next, we have a systematic sample. What is a systematic sample? How can we do a systematic? Pick a random starting point. You got it. Nice job, Adriana. Sample every kth element. Let's do that in the, there we go. That is a systematic. Every 4th passenger, every 10th passenger, every 20th. It doesn't matter what the K is. K is just used to space things out. So we'd sample every kth customer that comes through our airline. So that is systematic. Now we get into the ones where people make mistakes. These are where I see the mistakes every time. Clustering. Clustering works the following way. If I can type. Cluster sample. 1. Items or individuals are randomly assigned to clusters. Let's say randomly in clusters. You won't really be assigning them. You're not randomly assigning people to flights. But if you were to pick one flight, it's kind of the same as all your other flights. Basically, the flights are just a bunch of people. I want you to think how you can get a bunch of random donuts at one time. How can you get a bunch of random donuts? What would you get to get a bunch of random donuts? You'd buy a what of donuts? What would you get to get a bunch of random donuts? A dozen. What would you get to get a bunch of soda? A bunch of soda, you would buy what? If you wanted to get a bunch of samples of soda, now be careful. Don't think of one big sample, think of a bunch of individuals. Oh, don't worry, we'll get a 12-pack right there. That is a cluster, a 6-pack, you get it. That is a cluster. What is a cluster of students? Like a bunch of random students that you could just take all at once. Now, don't acknowledge a difference, but what is a cluster of students that you could just take all at once? A classroom is a cluster. Now, you might say, well, it's not completely random. It is hard to say whether or not the clusters are random, which is an assumption we'd have to have. But the classroom is a whole bunch at one time, and that makes it a cluster. So then what do? Select clusters randomly. Next, do a census on the cluster. So if you notice here, just like with donuts, if you buy a box of donuts, how many of those donuts are you going to eat? If you buy a box of donuts, how many donuts are you going to eat? You're going to eat the how many donuts? If you buy a box of donuts, you're going to eat 1 dozen donuts. Everyone's contemplating how many they'll eat, but you'll eat 1 dozen, 2 before you get sick. So you'd eat the whole dozen donuts. If you sample a classroom of students, how many students in that classroom are you going to sample? How many students in the classroom? And Hunter says all, he might have been talking about the donuts, and Jessica says all too. You're going to sample all of them. That's what a census is, so we're kind of reviewing what a census is. A census means you take everything from the population. Now, we're going to do a census on the cluster, not on the whole population, but when we take a cluster, like when we take that flight of 30 people, we will talk to everybody on the flight. So it might have said everyone gets a survey on the flight, but we're going to take a flight and then talk to everybody on the flight. The whole flight gets the survey right there. So now we go to, cluster sampling, and then stratified sampling. This is where people get confused. 1, acknowledge a difference, acknowledger, it didn't spell check it, difference in the population. 2, sample randomly within the strata according to that difference. And what does this all mean, to sample randomly within a strata according to that difference? You may say, Brian, that's a lot right there. Well, the first thing we have to do to stratify our customers is to acknowledge a difference. What difference might our flights have? Can you imagine a difference between flights? Like, what kind of differences are there between flights? Any ideas on how we could say, like, these flights are different from these flights? We have to come up with some way to say, well, these flights are like this, and these flights are like these. Like time length. Maybe some are red-eye flights, they're overnights. Airlines, maybe we're working for destination. Those are all different. Domestic, that's the one I like right there, because we have domestic and international flights. It's like those are 2 different flights. If we talk about your experience on a domestic flight versus your experience on an international, we could do it by airline. We can stratify by that. You're doing a great job because all of these are strata. So randomly sample economic, business, and first class. Yes, we could do it by like what level you flew with us. So who do you think we would have the smaller sample from? Remember, we're going to sample in the strata according to the differences. If we did, we're going to talk to economic, business, and first class. Who do you think we would have the least of? Who do you think we'd have the least of? First class, you're getting it. That is right. Because the way it works is if you think about all of our customers here, we could have, this is everybody we have as customers. So if 10% of our customers are first class, and then we have here, I think we had business and economic, then we have business right here represents, let's say 40%. So 40% is business, and then this is economy. So your job now, you acknowledged a difference, and your boss says to you, biz, we'll go biz right there. Your boss says to you, we want to sample 1,000 people. If you were to sample 1,000 people, then how many people would you get from economy, business, and first class? How many people would you get if you sampled 1,000? And you would get them randomly. You'd like randomly select these people. You would enumerate all the people, and then randomly. That's not a multi-stage. That's just doing it. 500 econ, you are right, because that's 50% of 1,000. Remember right here, we're going to do n equals 1,000. So what you would see is you would see econ would have 500, and then business would have 400, and then we'd be getting 100 over here. And we've now stratified sampled. So that, Jessica, nice job. All those answers in the chat, great job. We acknowledged a difference, because imagine if we only talked to first-class customers. Wouldn't that be a good way to or maybe they're really picky. I was gonna say, wouldn't that be a great way to have people be like, oh, it's awesome, but maybe they're really picky, and the economy people are like, I'm good, whatever. I mean, I just wanna fly. Or maybe the first class love it and we treat them really well. But right here, we are sampling according to that difference. That's what you do when you stratify. You sample according to the difference. Why would you not stratify on class that someone flies with on the airline? What would it mean if we said economy is a class? If we were to do that incorrectly and say, let's cluster sample economy, what does that mean we'd actually be doing if we're saying class, like economy, is a cluster? What would we be doing to economy if we treated it as a cluster in cluster sampling? We'd be taking right there, perfect answer, we'd be taking all of it. If you call it a cluster, you're saying take all of it. You're also telling me by saying these are clusters that economy, business, and first class are things that are kind of what, that people choose them kind of what-ish. Like those were kind of just, people were put into those kind of, at least a little bit, whatly. If it is a cluster, you're telling me that these things are what? They were put into them, because clusters need to be that things are just assigned at random. So these are not clusters. These are not clusters, these are strata, because you're acknowledging a difference, and that's the key between strata and cluster. Strata always starts by saying, I think people who fly on our airline might have different opinions if they're in economy, business, or first class, and then you could say, well, let's go and take 500 flights, and now we'd be doing a multi-stage. Because we go, let's take 500 random flights of economy, 400 random flights of business, and 100 random first, well, you can't take 100 random first class flights, so I guess this actually wouldn't work. Or you could take flights until you get enough of a sample. You could say, let's take a bunch of random flights to get the sample, and that would work, because you can't take random of one class, because the classes are across the airplane. But does that help make a little more sense on what clustering is, what stratifying is? This is the key difference right here. I hope people with this example kind of understand a little bit better how when we stratify, we acknowledge a difference. Great job, Hunter. And when we cluster, it's about things are put randomly into clusters. Then we take random clusters and we do a census on it. Key steps right there. How can you stratify soda? What way could you stratify soda? Any ideas on stratifying soda? What do you have to do to start to stratify? How would you do it to stratify soda? What characteristics can soda be stratified on? Let's see a bunch of those answer chats. Brands, Coke versus Pepsi. Different brands, diet, zero, regular. That's stratifying, that's acknowledging a difference. We could do, I think that's pretty much it. Diet versus regular, flavored versus non-flavored, Sprite versus Coke. Anytime you can basically say versus, I think versus is a good way. Like if you say, but you could say this class versus another class, but wait, this class versus another class, does that sound like you're talking about a difference? Or you have to say this class versus another class, this class versus one random class versus another random class? That doesn't sound. How about we talk about cherry versus vanilla flavoring? That's acknowledging a difference. Make sure it's really a difference, not just like class A versus class B. They'll have differences, but the differences probably are random. If it's just like random class A versus random class B, that's a cluster. But if you say cherry versus vanilla, that's actually acknowledging a difference right there, just flat out in cherry is not vanilla. These will be different, and we should maybe sample accordingly to it. Does that, I think we are good on that. We have, let's do the biases. Let's go down here to a new page and do some biases. Here we are with the biases. We have, to start out, convenience bias. Well, we did convenience sampling. It's convenience bias or convenience sampling. How about response bias? What is response bias? It's when the bias is in the response. This can be from the wording of the question or the person answering. So you have a lot of things here that people can ask where maybe someone is influenced to answer a certain way. You could be like, one of the ones on your My Pearson homework is like, do you think it is fair that you can go to war, that you can get married, but you can't buy alcohol till you're 21? And I'm not saying that is or is not fair, but the way you're wording it right there kind of pushes someone to be like, that is not fair. But really you're asking, should the drinking age be 21? That's the question. Or you could say, is it fair that the drinking age is 21? Even fair kind of implies something. Usually you want to go as unbiased as possible to not include response bias. Response bias is when you basically elicit a response from people or people are just not truthful. It's bias in the response, which it's really hard to clear that out. It's really hard to get people to be 100% honest or to write a question that does not influence somebody to answer a certain way. Like, I think another one on my Pearson is like, should companies that pollute and endanger the environment be responsible for cleaning up the environment? And then a better way of phrasing that would be, should companies have a responsibility for cleaning up the environment? Because any company could pollute or anything like that. You're not trying to be like, companies are polluting and endangering the environment. Should companies be responsible for cleaning up the environment? It's tough. It's tough to do good surveys. What is the bias when someone doesn't respond? It sounds to me like we got non-response bias from them. When individuals who don't respond differ in their opinion than those who do. So when we have non-response bias right here, people might be more likely or less likely to respond to our answers. Like imagine if I went out and had a ESPN banner and I was like, this is getting into a little bit of voluntary bias. Let's see here. I don't want to do voluntary bias. That sounds more like voluntary. Let's say I do a phone survey and I say, hi, we're calling you to talk about politics. And someone hangs up the phone. Well, the people who are hanging up the phone are probably not interested in politics. Since they're not interested in politics, their views on political issues might differ than the people's views who do speak to us. And this is a huge issue with doing political surveys. It's like, if you only speak to the people who will speak to you, well, then the people who don't speak to you might differ in their opinions than those who do. So you want to understand everybody, at least all individuals voting age or could vote. So all people in the US who vote, you want to understand them. But then when you have people who don't respond, they might differ in their opinions than the ones who do respond to you. And if you could just get everybody to respond to you and respond truthfully and sample the right amount of people, you would understand everybody pretty well. But this is the hard part of sampling. It's very, very hard to do. So yeah, this is very, very, very tough right here. How do you avoid non-response bias? If you were to do a survey and try to get non-response bias, and I think the elementary school one kind of has this, they say they send out a sample, they send out a survey and they make everybody respond. If I were to randomly select students and I were to say, what do you think about our new YouTube teaching method, which I hope you guys are liking. I love it. I love teaching you guys via this method. If you were to randomly select students and send out a survey to 50 students to talk to, like let's say this was going out to 1,000 students and I had a survey that was really long and I sent it to 50 students, I would follow up and try to get responses from them. Because maybe if 10 of them don't respond, that's because they don't like this. They're like, whatever, I'm not gonna respond because I don't like it and I don't care about this whole YouTube thing. So if you have people giving non-response, the counter to it is to get them to respond. You don't want people not responding to you and kind of making this thing where the people who don't respond differ than the opinion than those who do respond. Does that make sense? What non-response bias is when people are like, I'm not going to respond to this, and then they have a different opinion. Since you do not get a response from people who hang up on the sample, on the surveyor, is not representative of the population because people who hang up may have a different view. Yeah, that's exactly it. Nice job, Jackson. It's non-response because the people who are hanging up might have different views on the issues. So when you're like, oh, this was the views of the people who spoke to us, well, you want to understand everybody. Do you want to understand those people who hang up the phone on you? You do. Since you want to understand the people who hang up the phone and they have a different opinion, your metrics will be biased to the people who talk to you. Hence, you have non-response bias. So the people who did not respond are different in the opinions than those who do respond. Let's go right here and let's go to voluntary bias. People choose to respond to you, and this is not representative of the population. So this is where I do my ESPN one, where if we had a tent where we were like, hey, come talk to us about ESPN. If there was some sports anchors here from ESPN, let's say, I don't even know who's well, I can't say like Shaq. If Shaq was here, everyone would be like running over to Shaq. I'd be over too. I'd be like, class canceled, Shaq's on campus. I'd be like, YouTube stream's ending now. And then we'd have Shaq appear on stream. This one can dream. But with this in mind, let's say it's, I can't think, what is that guy's name? I can see him. Skip? Is it Skip Bayless? Saying quietly now. I don't watch ESPN really ever. Former roommate of mine watched it all the time. But let's say there was some ESPN people here. Would anyone in chat want to actually talk to them? Would anybody, even one person, or maybe no one wants to talk to them? Yes, Jessica would want to talk to them. And Jessica, do you like sports? Would you want to, Stephen A. Smith, there it is, there we go, Stephen A. Smith, I remember him. So Stephen A. Smith, if he was on campus, you'd be like, hey, that's Stephen A. Smith, he's at ESPN. And then they're like, hey, we have a survey we want you to take. And it's about like, how much do you watch ESPN and all these things right here. So the people who were to walk up to this ESPN tent and take a survey are basically volunteering. It's not that other people are, they're going up to them and be like, hey, take the survey, and they're like, no, because that'd be non-response. It's the people who are volunteering to take the survey are putting in bias. So they're actually choosing to take the survey, which is not good if they want to understand UT students. They might say we want to understand UT students who watch ESPN, and then they might be better on par by talking to people who want to talk to them. But if they're doing like, here's the views of UT students on ESPN, then you can't have people who choose to talk to you. You'd have to kind of be randomly out there and be like, hey, we have a survey and we want you to take it. And you can't be like, hey, we're ESPN people. And then people are like, ooh, I want to take your survey. Because then you have voluntary bias. The people who are choosing to respond to you are not representative. This creates where it's not representative. The last type of bias we have right here is undercoverage bias. It's a real word, at least in our stats world. Undercoverage bias. With undercoverage bias, we leave out a certain group from our sample. Or let's say this, a certain group is underrepresented in our sample. It also means another group would be overrepresented in our sample. One of my favorite examples for this is, let's say I want to go and figure out if we should triple the money we're giving to athletics. Is it possible to ensure that there is no bias at all? That is a good sampling question for, like, I would say it is impossible. There's always going to be bias. It's so tough. You want to try to limit as much bias as you can, but even good surveys have some sort of bias. And then Adriana had a question, wouldn't that be everyone who didn't respond to you because you wouldn't know if their opinion is different or not? Sorry, I hope I made that clear in the answers. Type it again, and if you want to, hopefully I'll clarify it. So undercoverage bias is when we leave out a certain group. And one of my favorite examples is, let's say we are voting to triple the money for athletics at UT. And you might, who knows, maybe people in the chat want to do that. So we go to Stokely, and we just talk to students leaving Stokely about should we triple the money for athletics at UT. Is that going to give us a representative view of what students think about tripling the money for athletics? Just we're going to go outside of Stokely and we're going to be like, hi, we'd like to take. No, wait, students live in Stokely. That's where students live. Students are in Stokely. Jackson says no, and just, why is everyone saying no? The students are probably telling us the truth. They're not volunteering. That's where all the athletes live. Oh, okay, that's where all the athletes live. And nothing wrong with being an athlete. It's just that you would undercover other students. So if you get too many athletes, you have too few non-athletes. So what would we want to do is we'd say, okay, we'd stratify by this. We would say, and we wouldn't get any off-campus students. You're right. You could say just the fact that it's all students living on campus. Yeah, I think Hunter said that too. Nice job. Because one, we have students who don't live on campus, and two, that's an athletics dorm. So this is where you'd probably say we need to stratify. It's not pure athletics, but there's where most of the athletes live or who live on campus. And so you'd say, okay, here's what we need to do. We need to stratify. We need to get students from off campus. We need to get students who are non-athletes, and we need to be representative. We can't, because if we don't have any off-campus students or we don't have any non-athletes, we're not representative. So undercoverage is when you get too much or too little. By getting too many athletes, we'd get too few non-athletes. So that's the way it works, is if you undercover something, it's because you over-covered something else. So undercoverage, you wouldn't call it over-coverage. The bias is that you left out a voice. So it's bad to leave people out of your survey if you want to understand them. We don't want to just understand athletes. We don't want to just understand non-athletes. We want to understand UT students, which is a combination of athletes and non-athletes, so we need to get the right amount, and we need to not undercover any groups. Does that help make more sense of all these biases right here with some key examples which we can talk through right here? But that is all the different biases. And let's define our last few words here, because we've covered a lot of this chapter right now, and then we'll go to some other examples. Our last few words that we should define here are going to be population, which is every person or thing we want to understand. In those previous examples, it was all UT students. Next, we have a sample frame. All people or things we have access to sample. I want you to put it in the chat. In that previous example where I had under coverage, what was my population? What was my population in that previous example? And you could say it as though it's a population. You could say, Brian, you wanted to understand who? You wanted to understand who? If it's the population, it's every person or thing I wanted to understand. So what was the population in that previous example? What was it? It was all UTK students. That was it. And then what was my sample frame? What would be my sample frame in that question? The question where I did an undercoverage bias, Jessica, you are right. The sample frame would be students that live in Stokely. You could technically say students at and around Stokely, like maybe someone's like visiting a friend or eating there. I'll see. We got audio in. Oh no! Oh no! Oh no! I need someone to help out. Oh shoot! We're peaking. Okay, there we go. Okay, we're back. We got audio levels. Okay, it's good. Thank you. Jason is taking over the stream.
So weird.
Jason is dressed. They like it. They say Jason is dressed up. Oh, here's Jason. Thank you, Jason. Jason is clean shaven. Jason's dressed up. I'm fading away. I'm out of the lights. Okay, we are back. We are back. Thank you, everyone. Everyone's like, audio's out. That's why it's good. Are the audio levels still good? I turned it down just a tiny bit because we were peaking. But okay, cool. We are good. It was on 2. It was on 2 when I came in. Thank you, Jason. We are good to go. We got batteries just ready to go, but we're using wireless mics. So, exactly. So the sample frame is all people or things we have access to sample. But then, what is the sample? What would be the sample in my previous example? What would be the sample in my previous example? Like if you were to say to me, Brian, your sample is this. What would be the sample in my previous example? I and you. So there we go. I and you, just trip over them. All people or things we get information on. So what is this right here? All people or things we get information on. So the sample frame was all students coming in and out of Stokely, where the sample is all students who what? The sample is all students who what? Actually, and I want to be clear because everyone, I think people forget, not all who live in, it could technically be all students who live in Stokely, but the sample would be what? All the students who spoke to me, all the students who answered, all the students who responded to me, everyone I get data from. So everybody, but freshman, There you go, right there. All the good food on campus. So all the students who actually speak to me, all the ones I get info on, the population was all UTK students. The sample frame were the people I had access to, the ones coming in and out of Stokely. Now that doesn't mean I spoke to all of them. The ones who spoke to me would be my sample. Let's do another example here real quick again. You are going to work for the Coca-Cola factory. So you now work for Coca-Cola. You decide to take a sample from the daily Coca-Cola. You take 10, the nearest, let's say 10 random packs of Coca-Cola and inspect them to see if they have damage and record what percent have damage. Okay, oh my God, oh. When I'm typing, I've got my hands like turned, so a little off the keys right there. So let's go through this problem right here and see if we can identify what is going to be the population. What is the population? What is the population right here? All Coca-Cola. So it's just, that is the population. All Coca-Cola being made. Coca-Cola, just you want to understand Coca-Cola. You could be specific and maybe say the Coca-Cola at your factory, or maybe we're trying to understand just Coca-Cola in general, but we have this right here. Next, we have the sample frame. And I like to do it this way. Population, sample frame, sample. They can all be the same size, but they can all go down. The only way they're all the same size is if you do a census and get everything. Then you want to understand everybody, you had access to everybody, and you took data on everybody, and that's a census. So a census is when you get data on everything in the population, which means you had access to everybody in the population, which means you wanted to understand everybody in the population, so you got data on everybody in the population. That's a census. But what is the sample frame here? What is the sample frame here? What is the sample frame? That, Hunter, that sounds like the, yes, nice job, Jessica, you got it. That is the sample frame. Because that is the Coca-Cola we have access to. What is the sample? What is the sample? What is the sample? I think, Hunter, you said it earlier. Great job. This is good practice, good review, and having these definitions down. This right here would be the sample. So this is the sample right here. We have the population, the sample frame, and we have the sample just going down the 10 random packs. You're getting it. So we have the 10 random packs. What else do we have? They're going to record if there's any damage. So the percent that have damage, what does that sound like? The percent that have damage. That's what they want to understand about their Coca-Cola. They want to understand the percent that have damage. Oh, no one said it. I need someone to say it in the chat. I need you to be thinking about it. What is this? It's what they want to understand about the population. So that would make that, well, the sample is our 10 packs of Coca-Cola, which is also a cluster sample. That's a cluster sample. It is the sample. Population parameter. The population parameter is what they want to understand. Now, we would have an estimate of that. So the estimate of it, so we could say estimate p hat. So the estimate of p is p hat. So let's write that way. Oh no, what did I do? There we go. I clicked a button. The estimate of p is p hat. So the estimate of the population parameter is p hat. That's why we make confidence intervals. Because think about this, if we only found like 2% were damaged, well, then we would make a confidence interval from that to say, well, I think between 1% and 3% are damaged. I'm just making up a fake interval. But the estimate of the true proportion, which is what we want to understand about the population, we want to understand what percent is actually damaged. The best estimate of that is p hat, which is right there. So the best estimate of p is p hat, and that literally brings us back to the notation we saw earlier. So what is the difference between population and population parameter if they both are things we want to understand? The population is the people or things you want to understand. The population parameter is what you want to understand about them. So think about this. UT students is your population. What might you want to understand about UT students? That's why it's population parameter. It can also just be called parameter too if you like, but population parameter if you want to say it fully. What might you want to understand about UT students? UT students would be your population. It's the who you want to understand. Then what would be different parameters we could understand about UT students? What would be different? I need some in the chat. What are different parameters that we could understand about UT students? Like different things we could be like, I'd really like to know this about them. Their major, maybe the proportion of UT students that are business majors. What else? Anything else we could want to understand? That'd be the population parameter there. What proportion of students are athletes? Where they live? What proportion of students live on campus? These are all parameters that we could understand. Sometimes it's also called the parameter of interest. It just means what you're interested in knowing. So you can hear it called population parameter of interest. All of these things mean the same, or when put together. Population means its own thing, but parameter is kind of the key word in population parameter of interest. Calling it the parameter of interest just means the thing you want to understand. And what you want to understand, the parameter, and who do you want to understand it for, the population. So parameter is kind of the key word in population parameter of interest. It just means the thing about the population you want to understand. What is that thing? The parameter. And in our examples, it was like, we want to understand the proportion who live on campus. That makes that the parameter of interest for the population. Does that help make more sense about what a parameter is and what a population is? Population is just everyone you want to understand, and then parameter is the thing you want to understand. So when you look at population parameter, it's the thing you want to understand about the population. So I hope that kind of puts those words to a little more sense. I hope you say yes or no in the chat. And I think that kind of does it for sampling review. So that's kind of, if there's, we'll finish up on sampling review here. We're just trying to do as many topics. Linda, great job, thank you. I'm always like trying to respond to you guys and keep the chat going because you guys are the reason I'm here to answer your questions. You're welcome, glad to help out. I want to keep answering as many questions as I can. I think there was, oh no, I'd never want that job. I would be like, nope. So Pete Buttigieg and I are like the same age. So you second that. We'd live in a world of video games if I was president. You may want that, but probably most people don't. I'd just be like, everybody plays video games now. That's my new rule, my new law. How can I use a TI? I got great news for you, Andrew. Well, one, you can use a TI to find the TI to find the z-scores. You can. I'm going to write that on here real briefly. I don't want to put this in the video. I'm going to say it. Here's the great news. On a test, we're going to tell you the z-scores and the t-scores. So, and let's review how to find the z-scores. One, on the test, we will tell you it. We will tell you a 90, or let's do 80%, has a z-score of 1.2815. A 90% has a z-score of 1.645. A 95% has a z-score of 1.96. Probably a lot of you know that if you've been doing the assignments. 98 has a z-score of 2.3263. And 99 has a z-score of 2.5758. 99.7, anyone got any guess what the z-score for a 99.7% confidence interval is? If you notice how the numbers are going, 99.7, and then we'll do some of those. We might, 99.7, what are the z-scores for, what's the z-score for that? It's basically what? That one's basically 3. Because 68, 95, 99.7, I don't know if I have enough room to write the 68 on here, but if we were to have 68, that'd be basically 1. And the 95 is more exact. If you notice, it's basically 2. On the test, we will give you these. And we really never make a 68% confidence roll. Oh, I think you put it in, because Andrew, if you put it into the calculator, then you will notice it's not that. Andrew, do me a favor and put this in. Put 99.73 in. Now you'll get 3. Oh, no, David and Lance, I thought. On the calculator, so here's the good thing. I've got some channel videos on the YouTube channel that show kind of how to do this. You want to use inverse norm. So I'm going to write this over here real briefly. To do a 99% confidence interval, it'd be inverse norm and then 0.005. So that is that one right there. That'll get that answer on the calculator because you're doing just 1 minus confidence level and then dividing that by 2. That's the number that goes into there. So it's half of the area outside the curve. Visually, it looks like this. If you were to take 1/2 of these areas. So that's the visual you're taking right there, is you're just taking one of those areas is what you're taking, and you're going to that portion of the curve, because if 99% is in the middle, you're taking that. And don't worry, you do not need to know this, and you do not need to memorize these. We will give you these on the test. I want to see 3 people got to say this in the chat right now. You got to say, they will give us these on the test. You got to put that in the chat. We will pause right here until people in the chat are saying, they will give us these. I want to see, they will be giving us these on the test. I want to see so many people writing that. So let's see it. They are going to give us these on the test. We will give you these numbers. They will give us these. They will give us these on the test. You got it. You know what I'm talking about right here. They will be giving, I like it right there. Sorry, Andrew, still working on the, you're right. No, Andrew, no, I love, Andrew, that is great. Andrew, keep up the great work. I know when you came by, I was really impressed because I like it when people are like, no, I want to solve this. And that's what I want to see. So I do have over here, this is, here, pretend that doesn't exist, but rewind the video if you want. That is a little bit of secret work right there. You got it. I see Caroline says they'll give us those on the test. You are right. You will get all these numbers. Let's show how you should do it on your homework assignments here. Let's go over to David M. Lane. So if you are stuck on the homework assignments right now and you can't find the z-scores, here's how to do it. Here is how to do it. Notice on this curve, it has a mean of 0 and a standard deviation of 1. Since it has a mean of 0 and a standard deviation of 1, everything on here is a what? It has a mean of 0 and a standard deviation of 1, making every single thing on this curve a what? Since it has a mean of 0 and a standard deviation of 1, everything on this is now a what? All those numbers below it are all what's? Mean of 0 and a standard deviation of 1, that is the standard normal curve, making everything on there a, oh no, z-score. The homeworks should be open still. The homeworks should all be open. They might be past due, but they should all be open. Please email me if they're not. Z-score, Adriana, nice job. They're all Z-scores. Maybe I should start giving out bonus. I can only give it to my students though. We do bonus for fun, but it's how to figure out close grades at the end of the semester. They're all Z-scores. If you notice right here, let's do a 95% confidence interval. So there's the 1.96. Here's the 1.2815. That's what the extra decimals are. And there we go, is that 95, 98, 99, and 99.73 is that right there. Andrew put in the chat and it was great. I was like, yes, you are right. It's 99.73. Because if you do 68, 68 is basically 1. And I think that goes to 1 right there. 95.449, and that's 2. Oh, got around to 45. And then 99.73 is 3. So 68, 95, 99.7. There you go. We just do bonus for fun. It's the last little bit at the end. But yeah, and thank you so much for being here. Jackson and Zachary and Karina, like I really appreciate everyone being here. I don't know how many people we have watching right now. It might just be 10, it might be 20, it might be 30, who knows. But I want you guys taking notes, and I want you to understand and watch how to do all these things. When is the next review? Monday night we'll be doing a Kahoot review. 24, I'll take 24. Thank you very much for all the answers and your interaction. This is meant to be as oh no, we lost someone! This is meant to be as interactive as possible. So what this is, how to find z-scores. Once again, they'll be given to you on the test. So You will get your z-scores on the test. We will give you them, and this is how to find it with the applets right here, which you will use for your homework assignments. So for your homework assignments, you will just use the David M. Lane applet, you'll do between, and you'll just enter in the confidence level. Like if it wanted a 96% confidence interval, there's the z-score for a 96% confidence interval. I know there were lots of questions, and this is the z-score down here. You only need one of them. What other questions were there? What chapters did people want done? Because we've done notation. We could do some probability. How do we go from z-score to the possibilities? Linda, do you mean how do you go to it? We'll do some probability next. I think that's a good idea. And how do we go from z-scores to the probability? Well, you'll take this z-score right here and you'll turn it into a confidence interval. So we'll go back over here to the notes for this, and that z-score will be used. Oh my gosh. Or let's go over to here to this. That's what happens when you copy over a PDF to a... I can't write on these, so I brought it over here. That z-score you see right there will be used in this interval, and then you will plug it in right here. Wait, how do you interpret a confidence interval? Great question, Hunter. Let's do this. Let's do an example confidence interval problem. So we're going to do an example confidence interval problem. You ready? So we're going to do confidence intervals here, and then we're going to do probability next. Does everyone have that? Right now it's confidence interval time, and then we're going to do probability next. This is a review of confidence intervals. This formula right here is key. And can I get this? We're going to copy paste this formula over. So let's go back to this. Let's go grab snipping tool. And let's grab this formula. Let's talk about how to use said formula. Now I can draw on it. The following formula is a confidence interval for what? The following formula, we'll probably go for another hour. I think another hour will be good. So we're going to keep going. We're going to go as long as we can, make this a great video. So what do we, it's a confidence interval for, it's a confidence interval for the what? Here's a hint. Anytime you're doing confidence intervals, you can always look at this. This is a confidence interval made from the what? What is that notation right there? Remember we did notation earlier? Watch that part of the video if you haven't yet. This is a confidence interval made from the what? Made from the sample proportion, meaning it's a confidence interval for the what proportion? So it's a confidence interval made from the sample proportion for the, to estimate the population proportion. You got it. So whenever you see the first thing right here, think about this. If you wanted to understand the percent of people who like Taco Bell, what would be your best guess? You'd go out and talk to people and you'd get a what as your best guess? You go out and talk to people to see if they like Taco Bell. And you want to understand what people really think about Taco Bell. I like Taco Bell. So you want to understand what people really think about Taco Bell. You go out and take a sample, and from this sample you would get a what? From this sample you would have a, what would you have? It's right here. From the sample you would obtain a sample proportion. I'll answer an estimate, which is the estimate. Because your best guess for the true proportion of people who like Taco Bell is the proportion of people who like Taco Bell in your sample. Imagine just for a moment, we're going to come up with a fake interval just to understand this. You would say, when I ran the statistics, 40% of my sample liked Taco Bell, plus or minus 10%. So 40% of my sample liked Taco Bell, plus or minus 10%. The plus or minus is the what of the interval. The plus or minus is the what of the interval. Everything in these intervals that we draw, when we do plus or minus, this is the center, the margin of error. You are right. So this is the margin of error. And go ahead and just try to solve the interval now. Be like, okay, the interval would go from this to this. And we could actually try interpreting this one just as a basic one. So right here, this gives us the confidence level. And this is the standard error right here, standard error of p hat. So the margin of error is made up of two components, the confidence level and the standard error of p hat. Those are the two components that go into the margin of error. That's the plus or minus on an interval. It's like 40% of people like Taco Bell plus or minus 10%, making 10% the margin of error. So I want you to take a moment and we'll just throw this big question out there right now. How would you interpret this interval? And I want you to just think about it. And whatever you write should make sense. Because you're going to be telling me about, you would guess that the something of the people who like something is contained in the interval blank to blank. And I'll give you a hint. Let's say that this z star over here was equal to, actually let's do it in a different color. If this z star used in the interval was 1.96, that should be, and that's the 95% confident. We'll pretend. This is good practice right now. If you are watching this video, please try to write this out. Remember, we're talking about the proportion of people who like Taco Bell. And I'll go and I'll show you the cheat sheet here in a moment for it. But we're trying to interpret it, and I want you to think about it. I want you to pause the video. You're like, no, I'm not pausing the video. Pause the video now. You want to say something like, I am. And let's go look at the cheat sheet. Here we go. We're going to look at our cheat sheet here. Remember this interval down here. Remember that interval. Let's go look at our cheat sheet for interpreting confidence intervals. Here it is right here. I am blank percent confident that the true, don't forget the true right there. And you could include it, that the true proportion of people who like Taco Bell is between the interval blank. Joanna, nice job, you got it. You used our cheat sheet right here to help out in interpreting that, I would guess. And I do the confidence, give the confidence. I am this percent confident. And so right there, so Jessica, little changes to it because you're this confident that the true proportion is between the interval blank to blank. So I am 95% confident that the true proportion of people who like Taco Bell is between the interval. Between or contained in is fine. There's other words we might not like as much, but right there, Joanna, amazing job. And then Caroline also gave us the blank interpretation, which is good too. This is an interpretation, but think about this. What are we saying with a 95% confidence interval? 95% of 95% confidence intervals are expected to contain the parameter of interest. You could even say in the long run, because 95% of 95% confidence intervals are expected to contain the truth. This is more of a description. So this is like right here, this is interpretation, and this is a description about confidence intervals. So this is a description about an interval, like 95% of 95% confidence intervals are expected to contain the truth, whereas when we interpret an interval, we're telling you what the interval means. But what all intervals, this is like all intervals, and then the top is specific to our interval. So there's kind of a distinction between what is the interpretation of an interval, I am blank percent confident that the true blank is containing the interval blank to blank, and then what do intervals actually mean? What does a 95% confidence interval actually mean? It means 95% of the time a 95% confidence interval will contain the truth, and that's kind of a long run thing, and truth being the parameter we are interested in. I'm 95% confident that the true proportion of people who like Taco Bell is contained in the interval 30 to 50. You are right. Let's do a harder problem now. Nice job, amazing job, everybody. Here we are down to a harder problem. Let's go here to a new page. On this new page, you decide to understand if UT students think, what are we going to talk about? Let's see. We need an IHOP on campus. You go out and talk to 100, let's not do that, 200 UT students who are leaving PCB. From your sample, 120 say they think we should build an IHOP on campus. We used to have an IHOP, you are right, and it went away. They kind of gave you PCB pancakes. You didn't get like really good pancakes. It's like, here's PCB pancakes that you can buy at IHOP, or you can go up to PCB and just get a bunch of pancakes. And I was like, yeah, this is not a good deal, in my opinion. Right here, build a 95% confidence interval from this data. Awesome. Let's do it. So, and let's do a few changes right here. Okay, I think we are good right now. Oh, and you kind of got it. You kind of got it right there, Adriana. I did insert some bias. Yeah, it's not random. I will admit, let's say, let's change it. I made it biased on purpose. I was going to say it's not random, and also let's, who are randomly from across all campus and off campus. Okay, there we go. So now, now it is, now it's a random sample. Okay, let's do this as though it's a test question. You ready? Here's the practice. Condition 1, let's do check conditions. Condition 1, great job, I like it. Condition 1, what is condition 1 right here? Let's talk about our conditions. So we are going to check our conditions to start. You got it. The first condition is random. Random. It is met because the question says we randomly selected UT students. So condition 1 is met because we randomly selected UT students. So random is met. Condition 2, now I always say these in order. There's no real order to them, but I like to do it in this order for a reason. Condition 1 is random for a lot of these things we're doing for the last test, and they're getting it in the chat. And condition 2, I like to do as the 10% condition. And this is met. Why is the 10% condition met? And what does the 10% condition mean? They're saying in the chat. How would you write a sentence on this? I need you to write a sentence now and explain to me. Why? Less than 10%, what does less than 10% mean? You are correct, you are very correct. But what would you write on the test to make sure we know you know that the answer is less than 10% and it is met? What is it? What are we doing here? And if you're typing in the chat and you're writing it down, you're practicing for the test right now. So even if you're listening to me, try to write these down. Less than 10% of the total population was sampled. You are right. So less than 10% of UT students were sampled. So we would say here that 120, you could say 120 is less than 10% of all UT students. Serena, amazing job right there. Because the sample size of 120 is less than 10% of UT population. Boom, that's even, I'm changing my answer now. I'm taking your answer. So that is better. The sample of 120 students is less than 10% of all UT students. That's it, because the population is all UT students, and your sample needs to be less than 10% of the population. That is a clear A+ answer right there. Now, what do? I need to see it in the chat. We need to do something here. We need to take a moment. What do we need to do? My students should know, every time we get to condition 3, we're going to do something. You get to condition 3, and you just what? You need to do something. Let's write here, and they're saying it. Oh, they're saying the answer, and the answer is pause first. Don't put that on the test. Let me put this. Do not put, someone's going to watch the video. I'm going to delete pause, but we pause here because someone will watch the video without the audio and they'll be like, condition 3 is pause. No, pause, just let your brain slow down. Let your brain slow down. And that's a great question. How do you know less than 10% when you don't know UT's population? Oh wait, so what it is UT's population would need to have at least 1,200 students in it for us to sample 120, or excuse me, oh wait, 120 is not the sample. 200 is. Sorry about that. 200 was the sample size. I noticed as we were talking about it, the 200 is the sample and 120 is the amount of successes. So sorry about that little error right there. But the sample of 200 is less than 10%. So there needs to be at least 2,000 students. So what you would do here is say, does UT have at least 2,000 students? And if the answer is yes, then 200 is less than, no, I did too. I was like, yeah, that's the number I just wrote. But 200 is less than 10% of all UT students. And let's put a little note here. This assumes we have more than 2,000 students. Oh, it went right off the side. Let's say assuming. I like when it's on one line. Great questions. Thank you so much for asking them, because that's what this is here for. I'm not trying to go through as many problems as I can. I want to do as many problems clearly as I can. So I want you to know this condition inside and out. When you're like, wait, why does it work? It's that we sample less than 10%. So 200 would be less than 10% as long as we have at least 2,000. So that's like an assumption right there, which is pretty safe. You wouldn't technically need to write that last part. You could assume the reader knows that, or you're just stating that this is true, that 200 is less than 10%, but that's got it. So how do we know the third condition is a really good question I get asked a lot. How would you know the third condition? The third condition would be decided upon if the data is categorical or quantitative. What question am I going to walk up to and ask UT students? I'm going to walk up to UT students and ask them, should we build an IOP on campus? Is that quantitative, as in numbers they'll be responding with, or categoricals, as in a category response like dog, cat, North Carolina, Tennessee? Will they give me a category response? Or boom, you got it, they're giving me a category. They're saying yes or no, which is categorical. So don't look to this many people said yes, because that's a number. Look to what they're saying, which is a category response. They're saying yes. If I said, how many IHOPs should we build on campus? That would be quantitative, which would be weird. It's like, what amount of IHOPs do students think we should build on campus would be a quantitative response with, or if we have, should we build an IHOP is yes, no. And you're getting it. Nice job, Jackson, right there in the chat. It is categorical. Since it is categorical, the third condition will be success failure. The third condition, or fourth sometimes later on, is denoted by the data type. So when you look at this as categorical data, you say, okay, categorical is some form of success failure. And we need to see that, and I'll write this down below. We need to do NP hat is greater than or equal to 10, and also NQ hat is greater than or equal to 10. Both NP hat and NQ hat need to be greater than or equal to 10. So, you know what's interesting? Does anyone know what NP hat is right now? Because watch this, I'm gonna solve for NP hat right here. If we solve x over n equals p hat, and we solve for x, we would get that x equals np hat. If you notice here, this is just multiplying both sides by n. So guess what? np hat is actually x. So what do you think, how many successes were there in this sample? How many successes were there in this sample? Can you see it? 120. So you could actually go back through and solve that. I'll show how to do that in a moment here too. But 120 people said yes, and put in quotes, make it all nice. And 80 people said, sure, it all corrected, no. These are both greater than 10. Greater than or equal to, we won't, greater than or equal to, greater than or equal to. We'll never give you exactly 10 because even then it'd be iffy. And I do like to show something with this. I do like to show why, because why will kind of make sense. So this condition is met because we have 120 people who said yes, 80 people who said no. What do 120 and 80 equal up to? Here's a trick you can do. If you want to see if you got the right numbers right here, what should they equal up to? If you add these two numbers together, they should equal up to what? 120 and 80. You can see what it equals up to. They equal up to n. You will know you have the right numbers if you have that they equal up to n, because it's just the amount that said yes, the amount that said no. So it has to be, here's the, and if it's a little decimal off, it's probably just because of rounding. So don't worry if you get like 199.98, you're like, oh no, something's wrong. It's like, it's rounding probably. So that's what's happening right there. You could also have done this the following way. You could have gone down here. Oh, we lost our notation. So you could have, there we go. You could have said that p hat, x over n, is equal to 120 over 200, which is equal to 0.60. Then you could do 0.60 times 200 equals 120. That right there is the mathematics. Does everyone see I just solved for p hat? Because p hat is equal to x over n, and then you could do q hat by doing 0.40, just change the 6 to a 4, and then you will get the 80. Does that make sense how np hat is actually x? It actually took me like 3 semesters to realize. I was like, wait a minute, that's just x. It's just the amount that said yes in your sample. So you have to have at least 10 saying yes and at least 10 saying no. And people say to me, why does this all matter? Why does it all matter? Let's go here to Iowa, binomial applet. The whole point of meeting these conditions is so what? The whole point of meeting these conditions is so what? Why do we try to meet these conditions? If we meet these conditions, we can use the what curve. If we meet all these conditions, we can use what curve with this to see if it's normal. That's exactly it. We want to pass the random, the 10%, and the success failure for this one to make it normal, that we can use the normal curve. If you notice here, what is 1% of 100? 1. What happens? Look at this. As I get closer and closer to what number, it becomes more and more what? Did you see it? The curve, when I go from 1 success to 2 to 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10, the curve becomes more and more normal. Even if I go higher to like 20 successes, it'll become more and more normal. It's just at about 10 successes, it'll be normal. And you can check this with bigger numbers by putting in like 500. How many successes would we expect of 2% of 500? 2% of 500 is exactly what? 2% of 500 is exactly what? Is exactly. 2% of 500 is exactly that magic number. I'll see in the chat. It's the magic number. Do NP right here. It's P technically in this one, but we were using P hat for our sample. 2% of 500 will be 10, and that looks pretty normal. But bring this down to 0.02, and now you have 1, and it doesn't look normal. So here, if you notice the number down here, it's showing us how many successes we expect, and it's only 1, and it's not normal. But I just like this visualization because if we had something like this, that's very normal. So it's going to be where we can use the normal techniques on it, and that's the whole point. That's why we are passing these conditions. We're not using the binomial applet on this test, but I wanted to show you why are we passing these conditions? Why do these conditions matter? Conditions matter That's why we were doing all these. We're doing all of these to use the normal. If we pass all of these, we're good and we can model it with the normal distribution. If there's problems, we can't use the normal because it's not going to be a proper statistical test or metric via confidence intervals or any other metric. So we're doing all of this right here to use the normal curve. That is the goal with the conditions. If you don't pass them, then I don't know if you should be using the normal and I don't know if your numbers are right. So now we get to the confidence interval part of this. So let's solve the confidence interval. Now, I guess that's pretty good. Oh, we lost part of our thing. Okay, let's put this right here. Well, we have p hat. It said build a 95% confidence interval. If you're watching this part of the video and you forget how to get a 95% confidence interval z-score, we can go back here to the David M. Lane applet. Here's the David M. Lane applet. Just Google David M. Lane applet. He made a great applet right here. And we're going to go to the percentage one and put in the middle 95%. So please note what buttons I have clicked on the screen. I have area 95 for a 95% confidence interval. I have mean of 0 and a standard deviation of 1 because I want this to be the standard normal curve, which gives us z-scores because we're finding a z-score for the 95% confidence interval. And I'm doing between, and I could technically have done outside, and I could have done 0.05. Because if 5% is outside, that leaves 95% inside. And this is for Andrew. I could have put in 0.025, which is what you would put in if you're doing inverse norm. And technically it would be down here on this side, it'd find you the negative number, but negative, positive, either or. So right here, oh, we already have some answers. I like that. Oh, it's saying, oh, I think because it's got a bunch of numbers in it, show that answer. So there we go. Let's make you a mod now. Let's put add moderator. You're now a mod, so you shouldn't get any answers blocked like that. So with this right here, this is how we do it on the TI calculator, but there's a lot of ways of doing it. It would be inverse norm 0.025 for a 95% confidence interval right there. So the between 95% confidence interval right there. And I think we already have the standard area calculated. We'll have to check that out. So now we know, let's put down p hat equals, can't even think anymore, 0.60. That was obtained from up here. All I did was x over n for p hat. And then that makes q hat. Okay, we're going to play the p hat, q hat game. You ready? A lot of people ask me, how do you know p hat all the time? Oh, Jessica, nice job. You guys are, If you are doing it already, you're doing amazing. So p hat and q hat game. If p hat is 0.6, q hat is 0.4. If p hat is 0.9, q hat is what? If p hat is 0.9, q hat is what? If p hat is 0.9, q hat is point what? And I'm almost saying it, 0.1. You got it. P hat and q hat are complements of each other. You're getting in the chat. If p hat is 0.9, q hat is 0.1. It's whatever adds up to 1. You can solve it by 1 minus p hat, just so we know how to find p hat and q hat every time. So now let's write out that interval, and people are solving it, and great job. We would get here 60%, and let's write our z-score right here. Z equals 1.96. Let me erase this. Let me do it all in notation first. And then n is also equal to 200. Write out all your notation so you can see what you got going on right here. So we got our notation for the problem. There is our notation. And next but not least, we're going to write p hat plus or minus z. And that's just the confidence level. And then we do p hat times q hat over n square root. And then this would equal to 0.60 plus or minus. And then we go to 1.96, big radical square root, 0.60 times 0.40 over 200. And that is it. Whatever that solves to the answer. Let's break it down though. Let's follow it through just a little bit here, and then people have the answers in the chat. Thank you so much. And I like that people are writing it out, writing and practicing it, because that's what we want to see. We're going to bring up the calculator here, wherever the calculator went to. You know, I could always just go pin to taskbar, and whoa, we got the calculator now. That was when I found that out, when I was like, whoa, you can actually pin stuff down there? That's amazing. So let's go 0.060 times 0.40 p hat times q hat over n. It's not n square root, it's n square root of the whole thing. So this is the answer that is inside that radical right now. Inside that radical, the 0.6 times 0.4 over 200 is that answer I have there. So this square root is the square root of all this, and Jessica was right on. She knew the answer. That is the answer for the standard error. Now we're going to take the standard error, and so let's write this 0.60 plus or minus 1.96, and thank you so much, because now I can look up here, and we're going to take this and do 0.0346. Now I'm just writing it there, but I am going to carry every decimal. Great way to do the problem. And now I have found the margin of error. And I might have some good news, because we have one last part of this question once we interpret it. So 0.6789, oh, that's a cool number. Oh, a cool number which I don't know how to write. Can we not go back in time? Oh, maybe not. There we go. 0.6789. There we go. So with this interval right here, we're just going to do the plus or minus on it, which will give us the following interval. And we go here, we copy 0.60 minus it, and then we do 0.60 plus it. And I think they got it right in the chat. Yep, 53.2 to 66.8. So 53.2 to 66.8. And this can be as percent or as a decimal. Either way is fine. Just make sure when you're working the problem, you carry through it as decimals. Don't put it as percents. Work it through as decimals, and then you can change it to a percent afterwards. So you could do it as the proportion or as the percent, but we'll call it here the true. You could say the true percent or the true proportion. Either or is fine, and these answers are excellent in the chat right here. I am 95% confident the true proportion of people, so true proportion of students, UT students, who think we should have an IHOP on campus is between. So Carolyn, great job. Just make sure you change it to the true proportion of students and you'll be right on. If you made a little small difference like that, not that big of a deal. This is, I am 95% confident the true proportion of students who want an IHOP on campus is between the interval 53.22 to 66.78. Great answers right there. Now here's a really big thing. What if UT said we were going to build an IHOP if there's evidence that more than 50% of students want an IHOP on campus? Do we have evidence right now that more than 50% of students want an IHOP on campus with this? Do we have evidence with this interval that more than 50% want an IHOP on campus? Do we have evidence for that? Is there any evidence? Yes, because right here is where 50% is at, and it's outside the interval. So we'd have evidence at the IHOP. So we're getting an IHOP. That's awesome. We are getting an IHOP. Let's try one or two more questions on these because I want to highlight some key topics. I don't know what doing that to my text. Let's go down here. No. Can I not go to the end of this? Sure. We'll put it all on new pages. There we go. Okay, let's talk about this real quick. If we have a confidence interval, I think a lot of people are confused on confidence intervals. Because let's say in a confidence interval, you wanted to tell me you will get home tonight between 5 and 6. So you're telling me your confidence interval is between 5 to 6. I want someone in the chat right now to write the interval as an interval. So it's like a plus or minus interval with a margin of error. So try writing this interval as a margin of error interval. I want you to write it as though it's this plus or minus this. And then let's see how they found that. How would you do this as an interval? I'm going to get home between 5 and 6. You'd say, oh, well, I bet you get home around this time, maybe plus or minus this. How would you do this? Just think about, you might understand, like someone says, I'll probably get home tonight between 5 and 6. Well, how does it work? What is the interval written as an interval with a plus or minus? Who knows? Remember, be trying to work these out and figure out how are we doing this? How are we understanding 5:30 plus or minus 30 minutes? You are right. So this would be 5:30 plus or minus 30 minutes. That's what we have going on right here. Nice answers. I'll be home at 5:30 plus or minus 30 minutes. And we've all kind of said that before. We're like, oh, I'll be home about 5:30, about 30 minutes, I could be off. These two are the same thing. Those are the same intervals. So how did we do this? Well, let's do an easier example that's really easy to solve. You ready? I'm going to go buy a steak dinner. No, I'm going to go buy a burger. The burger will cost between $10 to $14. So what is that written as an interval? That as an interval will be written as, and I'll do this one for us, 12 plus or minus 2. You say, well, Brian, that's easy. You might be seeing it now. You might be seeing. But let's see how we're doing this mathematically. So when you look at it, these are the whats. Let's put some notation under these. These numbers here are the lower. These numbers right here are the upper. This number right here is the center. Well, that's the wrong color to use for that. It's too big. These colors right here are the center. And these numbers right here are the margin of error. A little color coding right there so we can make sure we see what we're seeing. So I hope that's showing up well enough for everybody. So we have here and they're kind of lining up with the numbers they go under. It just kind of flows with that pattern. The first number, the second number, the third number, the fourth number, all of that right there are the different numbers we're looking at. So with this right here, let's talk about the formulas. How can we find the center from the upper and the lower? I want you to look at the lower and the upper and think about what you did. You whatted them to get the center. So the center, if you were to say a formula for the center is merely equal to what? Think about how you could find it from the lower and the upper. What did you do when you were like, oh, add them together and divide by 2, you got it. So the lower plus the upper, add them together, divide by 2. That is the center. All you're doing is just averaging them out. If you see it up there, you're just averaging two numbers. You're just saying, well, 10 and 14 average to 12. Just look, you're kind of just meeting the middle. I think about averaging as saying things are coming together. So you are taking the average of those two numbers right there. Zoom out a tiny bit here. What do we have next? Now we have the margin of error. Well, it might help to visualize our confidence interval a little bit. The margin of error looks the following way. The margin of error is a plus or minus on the interval. So we have a plus, we have a minus. Over here is the lower, over here is the center, and over here is the upper. So we have the lower, the center, and the upper, and the margin of error is the plus or minus. So I want you to think about this. the margin of error is what of the interval? Think about the whole interval. The margin of error is just what of the interval? The margin of error is equal to what the length of the interval? The margin of error is just what of the interval? If you have the whole interval, it's just what of the interval? The margin of error is just, think about this. Here's the margin of error. Like the margin of error is one of these right here. It's half of the interval. See, here's the whole interval, here's the plus, here's the minus. And so the margin of error is going to be half of the interval. Here's the whole interval, here's the margin of error. It's just half of the interval. So to find the length of the interval, we can do the following. Upper minus lower divided by 2. And we're not averaging them now. We're finding half the length of the interval. Does that make sense? Like 14 minus 10 is how far they are apart. 14 minus 10 is 4, and then half of that is 2. So 14 minus 10 is 4, and then half of that is 2. That's half the length of the interval. So you're just finding out half of it. You're not averaging them anymore. But you could also do a formula for it where you do upper minus center, and you could also do lower minus center. Those are just additional formulas right there, the upper minus the center or the lower, upper minus the center or center minus lower. I reverse that one. It still gives you the margin of error, it just gives you it as a negative number. Center minus lower. We're running out of room. So the center minus the lower, I don't want to put it below it, I don't want people to get confused with that. Those are just additional formulas you could technically do. Let me zoom in a little bit on it now. Hopefully my handwriting's not too bad. But the upper minus the center would be 14 minus 12 or 12 minus 10 because you can just take those values right here like 10, 12, and 14. And this right here is a distance of 2. And this right here is a distance of 2. And the two numbers average out to 12. So just practicing problems like this helps you better understand what the margin of error is. It's just half the length of the center. So the distance the upper is from the center is this one right here. That's this distance here. And the distance the center is from the lower is that also 2. It's just how far away is the center from the lower, how far away is the center from the upper, same distance there. Does that help make a little more sense on what we were doing with these intervals right here? Just a little last review on confidence intervals. We actually feel like we covered pretty much all the chapter right there. What other, we probably got times for one more concept. I think probability people said they wanted. I think it was probability, maybe. When do we use success failure and when do we use large enough? So condition 1 is always random. Let's copy those conditions. Where did I lose those conditions to? Let's mention that. So when do we use success failure? When do we use large enough? So here we go. Let's take this. Oh. Copy it and we'll bring it down here to a new spot. Let's erase up some stuff right here. Okay, so when do we use success failure? Success failure is when things are categorical. So let's go here to home. Let's click the highlight text. And then let's go here, and we're using, are these the colors we used earlier? I think so. Nearly normal, or large enough n. We'll call it nearly normal later on. Large enough n. The sample size is large enough such that the distribution, it's just the sampling distribution of the mean. There we go. Okay, so this will help the question. Okay, so we have here 2 different colors. There is not 4 conditions, and let's put here what this condition is. Let's put here both NP and NQ, or NP hat and NQ hat, are greater than or equal to 10. Show mathematically. Okay. Did we sample? random Cool. Okay, here are the conditions, but if you notice I have color-coded the last few right there. I have color-coded large enough n, and I have color-coded success failure. If you are doing sampling distribution, it's NP and Q. If you are doing confidence intervals, it's NP hat and Q hat for the success failure. The success failure is either NP or NQ, and the large enough n is when it is quantitative. So the biggest thing right here, am I in blue? No, I'm in black. So the biggest thing here is that large enough n is quantitative. Quantitative. Sampling distribution, I actually drew it out right here. Sampling distribution of sample mean. So this right here is quantitative. It is the sampling distribution of the sample mean. And this one right here is categorical. And it is either the sampling distribution of the sample proportion or confidence intervals. So the red one right there is the third condition when it is categorical, like the question we did earlier, like, do you want an IHOP on campus, is categorical, and we were building a confidence interval, so it was NP hat and NQ hat for confidence intervals. And since if we did a sampling distribution one, it'd be NP, NQ. Can you give an example? Sure. Here, let's see if you can figure out the third condition for this. And let's talk large enough. Hint, that might be the answer to this one. We go out and we talk to 200 random UT students, and we ask them, how many games do you think UT will win next year? So we're asking them, how many games do you think UT will win next year? The distribution we get, or the distribution of this is usually right skew with a mean of something and a standard deviation of something. With what you're hearing with what I'm asking, what do you identify about this question? That we're going out and we're asking students, how many games do you think we will win? This question I'm asking is what? This question I'm asking is what specifically? It's a what kind of question? What kind of question am I asking them? How many games do you think we will win? It's quantitative, that's the first thing you should identify, and if you look, we got quantitative right there. So quantitative is on the slide, you're hearing it, you know that this is something we're asking them, how many games do you think we will win? And so the condition is large enough n. And the question might say, well, let's do it. Let's do a full question with it. Why not? The distribution of games UT students think we will win is skewed to the right with a mean of 8 and a standard deviation of, let's say 7, because then I can say 2. 7 with a standard deviation of 2. That might be a little large of a standard deviation, but we'll do it. We go out and talk to 200 UT students and find a mean of 200 random and find a mean of 6. Is this unusually low? Now be careful, or let's do this. Here's a trick, and I'm putting this here for a reason. This is going to be, let's do a first question here. Check conditions, draw the sampling distribution of the sample mean, and then find the z-score. If you're practicing problem at home, try to do all these steps right here, but I want you to do this right now. If you see something like this in a problem, boom, that's something you should underline. Sampling distribution of sampling mean. And then you know what you should do? You should go right over here to your formula sheet and be like, sampling distribution of sample mean. Wait a minute, there it is, the sampling distribution of the sample mean. That's literally what this says. You remember from our notation earlier? Y bar is the sample mean, so this reads the sampling distribution of the sample mean. So if you know how to read the notation, that's a huge help because the question just told you what formulas to go to. If you notice, we have a mean, we have a standard deviation, and look, a z-score formula, which I just asked you for. So the question is trying to tell you this is a sampling distribution of a sample mean. Now some people might say like, wait a minute, that's not the sample mean right there. It is. It's y bar, and y bar is the sample mean. So using these formulas right here, we will solve these problems. So make sure you know which formulas to go to on your page. And that was my clue by putting down the problem right there. Draw the sampling distribution of the sample mean and find if it's unusual with the z-score. It's also in the problem above because we're talking to 200 random students and we find a mean of this. So we're trying to check the mean of those students, which is a sample of 200. This is not one student. Now be careful. What would the z-score be for one student telling us we'll win 5 games? What would the z-score be for one student? Here's the standard deviation. That's mu, sigma, and this one is mu. I was looking at the 7 already. Usually I say mu and sigma. So what would the z-score be for one student saying we will win 5 games? Can you see it? It is exactly how many standard deviations below the mean. If one student thinks we'll win 5 games, that is how many standard deviations below the mean. So think here's the mean, and here's the standard deviation. It'd be a z-score, not 2. Think about this, observation minus mean over standard deviation. But I'm going to erase that really quick because that's not the answer to this problem. The answer to this problem is about the sampling distribution and not one student. Because if you notice here, one thing I haven't marked yet, this is n. When you do these problems, nice job, Joanna, and thank you, Jessica. Keep these answers coming. Keep answering as many questions as you can. What we have right here is when we work a problem, here's my tips for success. Make sure to mark as many things in the problem as you can. Go through these problems and write down all the notation. When you see that we talk to 200 students, that's n. When you see it has a mean of 7, mu. When it has a standard deviation of 2, sigma. Now, let's talk about what we have right here. We also have that it is skewed to the right, because we're going to circle back to that large enough n condition right here. Condition 1, I need to see it in the chat. We're going to wake everyone up in the chat. Condition 1 is what for this? What is that condition 1? Condition 1 is what? You just tell me the condition. Just condition 1, boom, boom, random right there. You're waking me up. Condition 1, random. Condition 2, 10%, as in we sample less than 10% of all UT students. And we kind of have a similar one. I think I said 200 again. 200 is less than 10% of all UT students. It's not always UT students, it's just in these problems. Thank you, woke everyone up right there. So we have condition 1, we randomly selected UT students, we pass. Condition 2, less than 10% of UT students were sampled because 200 is less than 10% of all UT students. Pause. Slow down, Brian, slow down. Those were the easy conditions, the one that we can just kind of always do random. We randomly selected less than 10%, and now we get to, was the question quantitative or categorical? The question I just asked was quantitative because we're asking how many games do you think we will win next year? So we're asking how many games do you think we will win? And this is a quantitative question. People will respond with a number. Since it's a number, it's a quantity, and the condition will be large enough n. This is the way large enough n works. What we have right here is that if the distribution is normal, n needs to be at least 1. If the distribution is skewed, n needs to be at least 30. It might say 25 in the notes, but it's, someone wrote 25 on the board earlier, and I was like, I think it says 30 in the notes. I could double check, but it's 25, 30, either or is fine. And here, if it's heavily skewed. And the reason, it's because there's no magic numbers. That's why you're like, wait, 25 or 30, which is it? Please tell me if you get something wrong in the test, if you put 30. But here's the thing. In my problem, I think I said it was what? We'll put some notes for this. I said it was skewed. So let's say this. Right here is going to be normal. Here is skewed. Here is very skewed. What do you notice? What do you notice about what n needs to be the more skewed it is? The more skewed it is, the wider n needs to be. Kind of look to it. What does the large enough n condition mean? The more skewed it is, the whatter n needs to be. The more skewed it is, n is larger, the more skewed it needs to be. Not that n will be larger, n needs to be larger. So the more skewed it is, the larger n we need for the distribution of the sampling to be normal. So let's go right here and do this. Central limit theorem applet. What the central limit theorem states is that if n is large enough, the distribution of the mean will be normal. Now it also says it'll be tighter, but it does say it's normal. So that's a key thing. We're trying to highlight here in this moment that one of the key aspects of it is that if n is large enough, it'll be normal. Tell me, is taking a sample of 2 from this and averaging them large enough for the new distribution down here I'm building? Will this magical new distribution be normal, yes or no? If I did this a whole bunch, I'm taking 2 points, I want you to see what I'm doing. I'm taking 2 points and taking the average. Do you see how that falls in the middle? Will this new distribution be normal that would be built down here from the average of 2? This is the original distribution up here. Whoa, I didn't mean to do that. It will be. Reason being is the original distribution is normal, so the new distribution will also be normal. Remember, if that it's normal, n can be 1. It's not that it has to be 1, it's that 1 is large enough. So 1 is large enough that the new distribution will be normal, so 2 is fine also. I mean, 1 is the original distribution, and that's good enough. How about this one right here that is skewed? Do you think 2 is large enough? Will 2 be large enough here? I think this is skewed, so I'm going to average together points from here and make a new distribution, which is the average of 2 points. Every point down here is the average of 2 points. You see how that's the average? It drops? No, because it's skewed. That one's still skewed. Now, 25 does work for this, because watch, we're going to take 25 points, 25 different points, and take 1 point from them. That's the average. Is that new distribution normal? Yeah, because 25 was large enough. And that's why 25 and 30 are kind of like, tomato, tomato, because there's no magic number. And when we say skewed, well, how skewed do you mean? Well, what if it was very, very, very skewed? Let's go here to custom. So what does n need to be if it's extremely skewed? If it's ridiculously skewed, what does n need to be if it's ridiculously skewed? How large does n need to be if it's ridiculously skewed? 100. So will this be normal when I take 25 points and make a new distribution, which is the average? See, it says distribution of means of sample size 25. Will that be normal? It's still got that right skew tail to it. Do you still see that right skew? That might not be normal enough. I mean, it's getting more normal. It needs to be larger. You got it. That was not large enough. This one's so skewed that we need an n closer to 100, which this applet won't let us do. But the more skewed it is, the larger n needs to be for us to get normality for the distribution of the sample mean. This is the distribution of the sample mean. The original distribution has its own shape, and this is the parent population. So this is original distribution. This is your sample size. And it's not saying if I sample 100, the sample of 100 will be normal. It's the distribution of the mean for 100. Please take note that in this applet, what you're seeing is every blue dot down here is the what of 25 dots. Every single blue dot is the what of 25 dots. Every single blue dot is the what of 25 dots. Every single blue dot is the what of 25 points, 25 dots. Every single blue dot you are seeing is the average, making this distribution you see down here the distributions of means of sample size 25. So that is the distribution of means of sample size 25. Tell me, is this distribution really skewed? Now, skewed means tails a lot of times, like skewed is a tail. This one's not skewed, it's uniform. So guess what happens here? If we have a sample size of 2, well, this will start to look more normal. It looks more normal. How about at a sample size of 5 when we average together 5 points? Well, you'll notice even more normal. Frankly, that's kind of normal right there. We could use normal on that. How about 25? That looks perfectly normal. It looks just like the normal curve. So it usually has to deal with skew. The more skewed something is, the more outliers it has, the larger n needs to be. This one doesn't take a very large n because it's not that very skewed. And there's a lot of nuance exactly how large does n need to be. And we have a lot of ways of checking this in kind of upper level statistics with QQ plots and Shapiro-Wilk tests, all that great stuff, the omnibus test, I can't remember the other ones, but so many great tests and statistics to do this. But right here, we're just seeing if n is large enough, because what do we want to use? We want to use the normal curve on it. And if n is large enough, the distribution of the means, the lower one here, will be normally distributed. So this is the central limit theorem, which states that the distribution of the mean will be normal enough if n is large enough. That is one of the key things it says right there. So do we pass or fail the condition? What would you write on a test? Take a moment and tell me, do we pass the large enough n condition here and why? And I gave a key thing that should tell you whether or not we pass. I underlined it up there. I'm going to underline it again, and I want you to tell me, do you think we pass? Let's highlight it. Highlighter's fun. And then what you should look at is here. Do we pass? Do we pass, yes or no? Yes, because we have 200. And so be specific. You are correct. Jessica, that'd probably be good on the test. And let's be very specific. Let's put some notes here on this. Well, pass, because 200 is even larger than 100. Yes. Here's the 3 things I would write. You ready? 1, state the shape. 2, state the rule. 3, state if we pass. So we're going to state the shape. The distribution is skewed to the right. So our sample size needs to be at least, you could say 30 or 100, I could say very skewed, but the sample size is 200. So it's kind of either or, it doesn't matter. So you would say on a test, the shape of the distribution is skewed to the right. We need a sample size of at least 30, because I said skewed was 30. So we pass because our sample size is 200. It super passes because 200 is more than 100. So even if someone was more kind of conservative and was like, oh, we need a larger sample, it'd be like, oh, 200 is way large enough for something that is skewed. Even if it was very skewed, we'd need 100. So if you look up here, my wording for these were normal 1, skewed 30, and very skewed 100. So key stuff right there. So does that make sense on how we're saying we're passing the condition? Because now we can solve the problem. We got it. Now all we need to do is draw the distribution. So to draw the distribution, we're going to do the following. To draw the distribution, we are going to say that the mean of the distribution, wrong color, the mean of the distribution of y bar is equal to mu. The standard deviation of the distribution of y bar is equal to sigma over square root of n. And we've done it. Oh, Jackson, that is an A+ answer. I think the distribution is skewed to the right, so the sample size needs to be greater than or equal to 30. With the sample size 200, our data easily passes the condition. That is an A+ answer. Yeah, sometimes we usually state if it's skewed or very skewed. We try to make it clear, or if it's normal, and we try to make the conditions easily passing or easily failing. We like the conditions to be as easily identifiable on the test as possible. We'll not try to do like the sample size is 28 and it's skewed. You'd be like, wait, 25 or 30, which is it? We want you to kind of understand pretty quickly if it's good or if it's bad, and then we'll know if you know the condition. We're not trying to catch someone in the nuance of, is it or is it not? We don't want a gray area. We want a very easy to identify condition where you can be like, yes, and that's why I chose this one, because 200 is way large enough even if we had a standard of 100. So you'd be like 200 is large enough, and then even citing the number is what I like to do. That's a great way of answering the question. So great job. And you notice what we did right here? Look at all of our notation. We know the answer because mu y bar is equal to 7. And then standard deviation, y bar, is going to be equal to 5 over square root of 200. So let's do that. There we go. Oh, I lost my calculator. 5 over square root of 200. We got a 200 square root. And then 5 divided by it. And that's 0.03, 0.35. There we go. Can't say it today. 0.035. We're going to round it to that for the time being. It was a 6, I think, so let's do that. 0.036, we round it. There we go. That is the standard deviation, or excuse me, yeah, this is the standard deviation, not the standard error. That is correct. Why did you use 5 instead? Oh my gosh. You didn't see that. Rewind time. Been working too many problems. That was a test to make sure you're paying attention, Jessica. That was a test right there. That is when you know how to work problems and you use the wrong number. You did a great job, Jessica. Thank you very much. 200 square root. Just rewind time right there. I get one problem wrong a day and you caught it. You were right. That was the problem I got wrong. So there, that is the answer. Great job. Thank you for catching that. I was like, why did I use 5? You're right. So we got this. Thank you very much. If you're watching, if I snip these videos, this is the start of hour number 3. We'll be ending here in about probably 20 minutes or so. I'll take some more questions, but I'm going to chalk it up to that. One little error, that was sigma over there. So let's draw the distribution right here. What goes at the center of the distribution? The mean, which is going to be 7. And then, wow, this is going to be way off the distribution. So if you notice, I'm just going to use these standard deviations right here, 6.86, and this will be 6.72, and this will be 6.58, and then this will be 7.14, 7.28, 7.42. And I think I did it all correctly. All I'm doing is just adding and subtracting. Do you even see 5 on this distribution? Do you see 5 anywhere on this distribution? I just drew the distribution for the sample mean. This is the sampling distribution for the sample mean for what we would expect given 7 is the true mean. If 7 is the true mean, that goes right here at the center of the distribution. And then the standard deviation is the original standard deviation over the square root of n. So we have this all right here. You can see the standard deviation just going up and down that amount, which is this number all right here, just going up and down that amount. And then we have 7 at the center because if UT students say we'll win 7 games, well, that's what we would expect. And this isn't for one student, this is for a sample size of 200, making it the distribution of the sample mean, the sampling distribution of the sample mean. What you were seeing previously is the distribution I just drew is the blue one right there. That blue distribution is the one I am drawing right now. Does that make sense to everybody? I just drew that blue distribution for what I have. My original distribution up there was skewed to the right. It may have looked something like this right here, but my new distribution with a sample size of 200, not the 25 it says here, is going to be tighter and more normal due to the central limit theorem. And so we get the new distribution, and it's not the old one. The old one is still skewed to the right, and if I were to sample 200 observations, those 200 observations, pretend that's 200, would still have the right skew. You can see the black dots up there, still have a right skew to them, but the average of 200 observations to make a distribution of sample means will be normal and will be tighter by a factor of square root of n. And that's what we've done for this problem. The last but not least part of this problem will be to z-score our answer. It said, is 5 unusual? Well, we just need the formula that the z-score for this is going to be equal to our sample mean minus the mu of y bar over the standard deviation of y bar. And so we solve this to get that we do 5 minus 7 over 0.1414, I think it was. So let's go ahead and solve that. That's going to be ridiculously small, or like very negative. So we go here and we go 5 minus 7 is negative 2. We divide that by 0.01414 and we get negative 14.144. And this is equal to negative 14.144. Now, if the test asked you, is this very unusual? Is that a very unusual z-score? Is that very unusual? Is that very unusual? A z-score of negative 14.144? Think about this. When you look at your curve, can you see 5 on this curve? Is 5 would be way off the curve. 5 is so far off the curve that this is extremely unusual. You can't see 5 at all. It's so far off the curve that this is like way unusual to see. So 5 would be very, very unusual. The probability of it is basically 0. What if in our sample we saw something like right here? So let's say in our sample, let's change the question and change this. Now, why did I pick 6.86? What do you notice about 6.86 now if that is our y bar? That's what we saw in the sample. That's the sample mean we observed. So what do you notice about that 6.86? Let's go back down and look at our curve. Where is 6.86 on the curve? 6.86 is at a z-score of exactly what? Where is 6.86? It is in the normal, and it's on a z-score of exactly -1. So can anyone tell me how much area is below that? I don't know why that keeps doing that. How much area is going to be below that right there? How much area will be below that? What would that blue thing say? How much area will be below that? Let's try this. So if we want to find the area below that number, $16, you got it, nice job. And we found that because of the following. 68% inside, then that leaves 32 total outside, so that leaves 16% and 16% right here. That is what we have going on right here. We have below, and below -1 would be 16, and that's where we landed. I just changed the problem so we could actually find a percentage. The other one is basically 0. It's so far away that it's so many decimals that it'd be basically 0. But that will be asked to find the percent. You could, if you are, it's probably going to be, it could be something like this. I can't say it will be, but I'm just trying to go over some stuff that I think might kind of show you some tools and techniques, like how we can solve stuff by hand, that if you were to find something that had a certain z-score, you could plot it, you could draw it, you could see what's going on, and yeah. What other questions are there? You could be asked to do this. Everything I'm doing right now, you notice I did this without technology. A lot of people often ask, like, how can we do this without the David M. Lane? Well, this right here, I did it with the empirical rule. Using the empirical rule, I knew 68% was between -1 and 1, and then outside is 32, and then that leaves 16 in either one of my hands. So that's what we have going on right here. And I do want to mention, let me do something real quick before we finish. We'll mention a few other things. Let me hop back to this one. And let's pull up and let's go to playlists. Okay. Cool. Okay. Here we go back. Let's go back. Liked videos. There we go. So if you notice right here, we have playlists. Some of you may not know this, but there are videos going over many of the topics, like Test 2 chapter reviews. So there's a playlist right here you can watch that has a bunch of the review, like probability review, all of these right here, just sampling methods reviews, randomness review, decision tree reviews. We've updated this since, like, I know I'm using an older one. Oh, we're live right now. That's cool. It says that. I didn't know it would say that. Oh, look at that transition right there. I was like, cool, new transition. There's also, did you know that there's videos for many of the assignments? If you go to Test 2 assignments, you can find, or Test 3 assignments. So when you're working on the assignments for the end of the semester, sorry if the chapter numbers are weird. They keep changing the chapter numbers on us every semester, and then I have to go in, I'll update them, and then literally they'll change it another semester. I'll be like, okay, if you notice, hey, it's a confidence interval. So you can watch more videos, especially this weekend, of me working through problems right here, talking about different things. That one is on this playlist. I should move that to the other playlist. And so if we go here to Test 2 assignments, you'll see everything right there. There's summer test, so don't look at the summer test. All chapter review, spring 2019 lectures, Test 2 assignments. So there's videos right here going over things like your randomness questions. So you can see right here where I'm solving each of the different questions, kind of talking about how to do them. So it can give you some good help and kind of explain to you what's going on with these questions. I think a lot of you maybe know that because you're on the channel, but I just wanted to point out that there's playlists, and I try to keep them as organized as possible, and then the book changes a number, all that stuff, and there's me kind of looking down right there or something. But any other questions about what is going on, there's project playlists, there's the new normal curve video, we got the lightboard video. Also, lately I did some videos for, see there's the unlisted videos. You can see, there's a test stream we did. That's when we had the one problem. But we've got other videos here, like where I go over sampling and stuff like that, which is project, yeah, all this stuff. Any other last questions about what is going on? There's randomness one. So I just wanted people to know, if they didn't know, if you're watching this video, that there are videos on the channel where I go through. This was the one where people go to a party. And so I talk through this question and explain how we solve it. And it's like a 9-minute video, but I explain the whole question and I go through and solve a version of it. And so, yeah. Any other, oh, chat's not scrolled down yet. Let me see if people are saying anything in the chat. Okay, there we go. That was cool. Oh, good. I like that you, yeah, I'm just kind of winding down here. I really appreciate everyone who stayed this whole time. We should see crash. We should, yeah, I don't know. What does everyone think? What should we, any other last questions about what's going on? I'm probably gonna head off here in a moment. You're welcome, Jackson. We should end with a really fun video to end. Let me end with a fun video. Let's see. Let me change this real quick here. Oh no, I can't change it without it. You're welcome, guys. You're welcome. I don't think I can change it. What is on the Batman thing? Oh, there's the...
It's not the question you deserve. It's the one you need.
You're welcome. You're welcome. I'm trying to see what we have here. I got all the buttons. I can always just press all my buttons. You can't see it. Oh, it's off the screen. So end with a donkey video. I wish we could do that. But no, thank you guys very much. Yeah, I wish we could. If we ever got someone like that to help us out, because we could actually stream them in here. We could actually have them appear in the video. But thank you. Crab Rave. Oh, we need Crab Rave. Let me pull up Crab Rave. Let's end with Crab Rave. Let me get Crab Rave in here. We need to end with a Crab. We always end with a Crab Rave. We haven't done a Crab Rave in a long time. Let me find it. Where's it at? Oh no. Is it? It's underdone. Wait. Okay, 2 seconds. Got it. All right. Are you ready? Here we go. We're ending with a Crab Rave. We got this. Yeah, there it goes. It switched between it, but... Okay, guys, thank you very much. It is Crab Rave time. Have a great evening, and email me if you need any help. Bye.